Hello guys, I'm going to take you through Taylor's theorem. So my name is actually Kimboy Kibiwat Dennis. This is my registration number, that is E028-01-0873-2017. Our main objective from this topic is the derivation of Taylor's theorem. We are going to just derive the Taylor's theorem. So in derivation of Taylor's theorem, we need 10 functions. Since Taylor's theorem is a theorem that is used to find values of two functions. Now, for example, we have a function of x and y, or a function of a and b. So as you can see, Taylor's theorem is used to solve functions of two values. The values are x and y, or a and b. Now, our first function, we need to find function of x and y. So, our first function will be a function of a and b, whereby these are given values. This can be 0, 0, or 1, 1, or any other given value. It can be 2, 3, 4. Now, so the second function is a function of x alone, which we find it as x minus a. The second function is function of y, which we find it as y minus p. So this one will take a factorial, the inverse of 1 factorial. Then we add from the first one, this one, we add this one. Then we move to the next one, which is a function of x, a function of x and y, and a function of y and y. I think it is visible for all of us. So let us see, what will be this one? This one will be x minus a from the initial, x minus a, but we have two x's, so it will be x squared. Consider here also we have x and y. And for us to find this, we need the concept of linear algebra, whereby we shall have here two opening brackets. For the x, which was x minus a, that's for the x. And for the y, we shall have y minus p. Then we close the brackets. That shows that these two will be multiplying the whole functions inside here. And for the last one, we shall have y minus p cubic and square. Square, because we have two functions of y. Now, we move to the dots, whereby we have a function of x, and x. And before that, this one will take the inverse of 2 factorials, and you add to this one. That's why it's a series. It's very long. First equation, you add to the second, and you add to the third. This one, because we have 3x, it will be x minus a. Because of the 3x, we shall have it to be cubic. Then we move a function of x, and y. This one will be x minus a. How many x's do we have? We have 2 x's. So it will be x minus a squared. And for the y, we have y minus p. And from linear algebra, you realize that when you expand, you shall have 3 here. So you shall have 3 at that point. Then you move for the x and y. Also from linear algebra, you shall have 3. You shall have 3 opening brackets. For the x alone, we have x and we have 2 y's. So this will be y minus p, the square. Then you close. I've said this one is coming from linear algebra, this 3 and this 3, because when you open the brackets of a square, a minus a plus p, a plus p square, a plus p, you'll find it will refer us to these 3 and 3. Since you shall have a square plus 2ab plus b square, you multiply this one by a plus p. You realize that it will take the form of a into a square plus 2ab plus b square. This will be a cubed plus 2a square b plus a b square. Then plus, for the cubic p, shall have a square b plus 2ab square plus p cubed. So when you have these 2 and this one, you shall have 3a square b. 3a square b. That is where we find these 3 coming from. So this was unnecessary from us. So that's why we don't need them. Now the final one is the function of y, and y, which will refer to what was y? It was y minus p and cubic of it. So as we had said before, for a being 0 and p being 0, it will give us what is known as Maclaurin's theorem. But when the values of a and b as 1, 1, then you realize that this one will now define the Taylor's series. So when you substitute, this one you'll find, if you substitute it by 0, you get Maclaurin's, and when you substitute by 1, you'll get Taylor's. That's all about our derivation. Thank you for your listening. May God bless you so much.